Welcome to Lecture 12 of Electrical Engineering 525. As was probably apparent at the end of Lecture 11, Lecture 12 is just continuing along with the same notes. In fact, right here at the top of the page, you see the figure that was drawn to help explain the problem or the set of problems on test 11. And by the way, in the video, in video 11, when I drew this picture, I mistakenly let's make clear in the statement of the problem, the location of the right parasitic element was correctly written as 0.02 lambda. So this part was written correctly in the statement of the problem. But then in this figure, I labeled this as 0.2 lambda rather than 0.02 lambda. So I have corrected this now, and that correction should also be in the OneNote notes for this lecture. So anyway, that concludes a brief discussion then of what was going on at the end of Lecture 11. And now in Lecture 12, we're still in the same section, Section 3 of Chapter 6, and still looking at problems related to the Yagi Uda array, but now we'll look at something much more directly related than the problem set that we looked at in the previous lecture. So let's go ahead and read the problem that we'll be working on to help us to understand how the Yagi Uda is designed. So we're looking at problem 6.3-4, and it says that we are to design a 10.2 dBd gain Yagi for operation at 50.1 megahertz. The parasitic elements are insulated from the metal boom. The diameter of the elements is 0.0021 lambda. Now, one comment right away, we haven't encountered this unit dBd before, and that's decibels over a half-wave dipole. So this is just another way of measuring the gain. You can measure gain relative to an isotropic element, or you can measure the gain relative to a half-wave dipole. And when you measure the gain relative to a half-wave dipole, frequently then the units will be reported as dBd, just to help make sure it's clear what gain you have in mind. So in this case, then we have 10.2 dBd because we have we're measuring the gain relative to a half-wave dipole. And the first very important fact to note about this statement of the problem here is that the parasitic elements are insulated from the metal boom. And as is pointed out here, it says, first note that since the parasitic elements are insulated from the boom will have a negligible effect, and we don't need to use figure 6-26. As you will see, this problem will teach us how to use figure 625 in your textbook and also table 6-3. If the parasitic elements were not insulated from the boom is the support structure, and if the parasitic elements were not insulated from the boom, then we would also have to use, in addition to table 6-3 and figure 625, we would also have to use figure 626. But since the boom is insulated, that relieves us of that extra step in the work where we would have to use figure 626. So let's proceed now with this problem. Now, again, we want to design a 10.2 dBd, Yagi Uda with a 10.2 dBd gain, and the diameter of the elements is 0.0021 lambda. So keep those two figures in mind. The 50.1 megahertz, that will be relevant much later in the problem, but for right now, what's important is this 10.2 dBd gain and the 0.0021 lambda. So now that we've identified that we want the 10.2 dBd gain relative to the half-wave dipole, we first look in table 6-3 to understand how many directors this Yagi Uda array will have. So here is table 6-3 in your textbook. And what you should do then in a problem of this type is first look down here at this line where it says gain relative to half-wave dipole measured in dBd. And again, our goal here was to design a Yagi Uda array with a gain relative to the half-wave dipole of 10.2 dBd. So we're here in this third column. Again, because of this 10.2 here, we're in this third column. And so you can see that the boom length that we will want for this Yagi Uda array is 1.2, and keep in mind that this is measured in lambda. So we want a boom length of 1.2 lambda. And furthermore, we want 4 reflectors. And how do we know that? Okay, this first number in that column, the first number gives you the length of the reflector element in terms of LR over lambda. So in other words, LR, the length of the reflector, would be 0.482 lambda. Now keep in mind, before I go any further, let me point out that everything that is in this table is for a Yagi Uda array that is constructed from wires having a diameter of 0.0085 lambda. But in our case, of course, we are given wires of diameter 0.0021 lambda. So everything that we're looking at here in this table, we're going to have to, everything is subject to change except for actually the number of elements that we will have. So we're going to have to look at, let's see, we're going to have to look at this table 625 to make the appropriate adjustments for the fact that our element diameter is different from what is the case here in this table, but this table is a good starting point, and we'll see how this goes. So anyway, like I say, the one thing that is for sure is that the number of directors shown here will be the case that we want, even though the wires we're using have a different diameter from the diameter shown here. So anyway, if you look here, then this first number is the length of the reflector, and then the next 4 numbers are D1, D2, D3, and D4. And that tells you the positions of the excuse me, not positions, but the lengths of the directors. So the director D1, director 1 would have a length of 0.428 lambda. Director 2 would have a length of 0.420 lambda, Director 3 would have 0.421 lambda, and Director 4 would have a length of 0.428 lambda. But altogether, there are going to be 4 directors, 1 reflector, and 1 driver in this Yagi Uda array. So altogether, we're going to have 6 antennas, the driver, the reflector, and 4 directors. And that's to get this desired gain of 10.2 dBd. So this is the first step in a problem of this type, is to come and find your gain down here in this row, and that will tell you which column you're in, which will help you to decide the number of directors that you will have for your antenna. All of them have 1 reflector, but different antennas here, different Yagi Uda arrays, have different numbers of directors. Okay, so that's the first part of this problem. And that's summarized right here. It says, from table 6-3, we see that a gain relative to half-wave dipole of 10.2 dBd corresponds to a boom length of 1.2 lambda with 1 reflector and 4 directors. So here we have just what was described a moment ago. Here's your driver. Here's your reflector to the left of the driver. And here are your 4 directors to the right of the driver. And this is with the assumption that the Z direction here, we're wanting that for maximum value of the pattern. This is the 0 degrees or end fire direction. So now we want to get what we have to do, once again, just to make sure all of this is clear. Everything here in this table 6-3 is based on the assumption that the wires have a diameter of 0.0085 lambda. The length of the reflector is based on that. No, actually there is one other thing that is not based on it. This SR, now SR equals 0.2 lambda. That's the position of the reflector. That's how far the reflector is to the left of the driver. And as you will see, let's go ahead and look right now. In all of this information here on this page, you can see we have a number of different cases, A, B, C, and D. And you can see, you might notice that SD is different for different cases, but SR is never given here. So SR, the value of, and here actually, I believe that they show SR. No, unfortunately they don't label it, but SR, here's your driver, here are the directors, and SD is the spacing between the directors. SR is the spacing between the reflector and the driver. Or to look at it in still another way, going back to our picture, okay, the directors are equally spaced, and the spacing between them is S sub D. The spacing here between the reflector and the driver is S sub R. And for all of the cases we will consider, S sub R will be equal to 0.2 lambda, regardless of the radius of the wire. Now you can see also that although the value of SR is always the same for all of these cases, and even for the cases where the diameter of the wire is different, SD, the spacing of the directors, is different for different cases. Here is 0.2 lambda, 0.2 lambda, 0.25, 0.2, 0.2, 0.308. So we're going to have to keep up with this as we proceed with this problem. We need to keep up with the value of SD. SR is always going to be 0.2 lambda, but SD will be different for different cases. And then finally, just to emphasize once again, these values for the reflector length and the director lengths, all of these values are for a diameter of 0.0085 lambda, but that's not the diameter we have in this problem, and so that is why we need to go to figure 625. So now let's begin to understand how we will use figure 625. Okay, well, the first thing we'll do is to go ahead and find the reflector length. Now, the thing that I'd like to point out to you is that there are 6 curves here in figure 625. The top 2 curves are for reading off the appropriate reflector length in different cases, and the bottom 4 curves are for reading off the director lengths in the various cases. Now, it turns out that we have, let's go back here one more time to the this table. You see in the table we actually have 1, 2, 3, 4, 5, 6 different cases here. We have 6 different values of the gain relative to half-wave dipole that this table would allow us to design for. Now, this top curve could be used for the cases C, A, and B. Now, C is actually 3 of those cases from the table. Is the case where you have 3 directors, 4 directors, or 15 directors. All 3 of those cases are grouped together and labeled as C. D is when you have 13 directors, B is when you have 10 directors, and A is when you have 1 director. So since we had, again, from table 6-3, we had 6 different cases here, but they're going to group, as we see from the figure 625, we will group 3 of them together. And so since that is the case, since we're grouping 3 of those 6 together, then we have altogether 4 cases to consider in that figure. And that's why we get 4 different curves here for the director lengths. But it turns out that for the reflector length, we only need 2 curves because the top curve will correspond to cases A, B, or C, and keeping in mind that C is actually 3 different cases, so that means that this top curve takes care of actually 5 of the 6 cases, and D, this curve right here, is only used for the case of 13 directors. But anyway, so the way that we will proceed with this is, in the problem under consideration, remember that the diameter of the wires is 0.0021 lambda. And so we come down here to 0.0021, and you can see that the increments here are 0.0002 lambda, so 0.0021 would be midway between these two lines. Midway between this line, which is 0.002 lambda, and this line, which would be 0.0022 lambda. So midway in between that, and we'll keep moving up, and we need to stop. Now, by the way, which reflector curve? Because right now we're looking for the reflector length, and which one do we need? Well, remember that this one is for case D, which is the one with 13 directors, and this curve is the curve for all of the other cases. So this is the curve that we want, and if you look at that, that gives you a reflector length. Now you have to approximate this, but it looks to me like this is between 0.488 and 0.49, so maybe you'd say 0.485 lambda. So we come back over here, and actually I guess that let's see, when I did these notes, I approximated it as 0.488. So somewhere between 0.488 and 0.49. And so I'll just, obviously when you do the problem for the test, you're not going to get the different students won't all get exactly the same answer as each other or as me, but I'll leave the choices for the multiple choice questions. I'll make them sufficiently distinct from each other that we should all get the final same choice for the test questions. So anyway, we get a reflector length of 0.488 lambda. And I'll just point out, now remember that, well, let's see. If we go back to the table, to this column that we're talking about, the one where the gain is 10.2 dBd, if we had a diameter of 0.0085 lambda, then the length of the reflector would be 0.482. But in this case, it's 0.488. So you can see that the fact that we have a diameter that is different from that given in the table has made a slight difference in the length of the reflector. Okay, so that's the first thing to note here in this problem. And now, what about finding the length of the directors? Well, as you probably have already guessed, to do that, we'll look at figure 625 again, but this time we'll look at one of these four curves here. Now, we want the one that corresponds to the Yagi Uda array with four directors, and you see that that's this one right here. It's the second array listed under category C. The first one listed under category C is the Yagi Uda array that has a total length of 0.8 lambda and 3 directors. Okay, that's not the one that we want. We want this next one, the 1.2 lambda long Yagi with 4 directors. So this is what we want. And notice right here, it tells us that here's something to notice. Now, actually, this value is also given in table 6-3. So the fact that we, in the problem under consideration, the fact that we have wires of different diameter from those under consideration in table 6-3 actually doesn't change SD. And of course, as we've already mentioned, it doesn't change SR either. So in this case, we will use a separation between directors of 0.025 lambda. But now we need to find out what the lengths of those directors will be. And so to do that, we're going to look at this graph again, and since since the case that we want, the one with 4 directors, falls in category C, we will want to project up to this curve right here, this the third curve, the third of the 4 curves for director lengths. So again, we come up here at 0.0021 lambda, and we'll extend this up to right here to the curve labeled C, and it looks like that is at 0.452 lambda. And indeed, that's what I obtained before when I made these notes as well. So we get L of, now by the way, that is the first director. Okay, that's not going to be the length for all the directors. That's just the length for the first director. So the length for the first director is 0.452 lambda. And now the question is, how do we get the lengths of the other 3 directors? Because altogether, as we've already said up here, we want 4 directors. We have found the length of this first director. Now we want the lengths of the other 3. How do we do that? Well, let's go back. The procedure is described right here. Let's go back to table 6-3, which pertains to the case where the diameter of the wires is 0.0085 lambda rather than 0.0021 lambda. Now, if you go back to that table, you'll see that the director lengths given in that table are these, and that's 0.428 lambda, 0.420 lambda, 0.420 lambda, and 0.428 lambda. And let's go back to the table just to make sure you see where I'm getting those numbers. So here again, we're in this column, and you see 0.428 is the length of the first director, 0.420 is the length of the second, 0.420, and these are all in terms of lambda. So 0.428 lambda, 0.420 lambda, 0.420 lambda for the third one, and 0.428 is the length of the fourth director. So here are the lengths of the 4 directors in the case when the diameter is 0.0085 lambda. And so we've just reproduced that data right here. So now we're going to do a simple calculation. The length that we found up here, LD1, this is the length that we found from figure 625. And this is, remember, this is the length when we used the correct radius of 0.0021 lambda. The length that we found there was 0.452 lambda. Okay? But if we had been using wires of 0.0085 lambda, the length LD1 would be 0.428 lambda. So the fact that we're using considerably thinner wires has made a fairly large difference in the lengths of the directors. It didn't make a very big difference in the length of the reflector, but it has made a fairly significant, from 0.452 to 0.428, a fairly significant difference in the length of the directors. Okay, and again, this is the length of the first director, but how do we find the length of all the other directors? Well, the answer actually is let's just look at how much of a difference it made in the length of the first director, and then the same difference will occur for all the other directors. So in other words, if you look at this, 0.452 minus 0.428 is 0.024 lambda. So we're going to use a length for the first director that is 0.024 lambda longer than that given in table 6-3, And so we'll use that same point. We'll increase each of these by that same amount um, um, for the rest of the directors. And so that's what it basically gives you right here. It says LD1, the length of the first director, in the case that we want, which is the diameter is 0.0021 lambda, minus the length of the first director in the case. This is the case for table 6-3. Maybe I'll put that table 6-3, and this is problem under consideration. So if we take the length we obtained from, maybe you should say from figure 6.25. So if we take that length and subtract from it the length in table 6-3, which pertains to a different case, we get, as was mentioned just a moment ago, 0.024 lambda. And so, just moving this term over to the other side of the equation, this tells us then that the length of the first director, when we have this diameter for the wire, is equal to the length of the first director for this diameter wire plus this amount, 0.024 lambda. And so, as was said a moment ago, so for all the other directors, for n equals 1, 2, 3, 4, we assume that all of them will be increased by that amount. So that means that for the second director, since the second director from table 6-3 had a length of 0.420 lambda, now in this case it'll be 0.420 lambda plus 0.024 lambda to give 0.444 lambda. The length of the third director, in the table is 0.420 lambda, so we add 0.024 lambda to that to get, again, 0.444 lambda. And then finally, for the fourth director, the length from table 6-3 is 0.428 lambda, and that needs to be adjusted by adding 0.024 lambda to that to get a final length, for this case, of 0.452 lambda. And then finally, in the information given for the upper curve C in figure 6-25, it says that, and we've already noted this, that the spacing between the directors is 0.25 lambda. And actually I said here rather than 0.2 lambda as in table 6-3, but actually that's not correct. Let's go back and you'll see. For the case that we're looking at, the table actually did say 0.25 lambda for the spacing between directors. So actually, now it did indeed say 0.2 for this one and this one and this one and this one, but for the case we're looking at, it did indeed say 0.25, so there's no need for a change. So let me erase this remark because it's misleading. Okay. And so, and then resuming here, since no information is given for SR, which is how far the reflector is to the left of the driver, it is as given in table 6-3, 0.2 lambda. We've already talked about that. So to summarize that then, SR, that's how far the reflector is to the left of the driver, 0.2 lambda. SD is the spacing between directors, and that's 0.25 lambda. And D, of course, the diameter of the wires is given in the statement of the problem as 0.0021 lambda. And so now that we have this, and now we finally take into account the frequency of operation, which is 50.1 megahertz, and at that frequency, lambda is equal to 5.988 meters. And so this position of the reflector becomes 1.198 meters to the left of the driver, and SD is 1.497 meters. That's the distance between consecutive director elements, and the diameter, remember, is 0.0021 lambda, or 1.26 centimeters would be the diameter of the wires in this Yagi Uda array. So that summarizes then how you use Table 6-3 and Figure 625 to design a Yagi Uda array for a desired gain relative to the half-wave dipole. And so now to test your understanding of this technique, let's look at this problem, and just as was the case, this will be now test, not test 11, but this will be test 12. So test 12 and problem group 1, and we'll, as was the case in test 11 before, we'll develop probably several problems from this one situation, but the situation is this: design a 9.2 dBd gain Yagi for operation at 40 megahertz. The parasitic elements are insulated from the metal boom, and the diameter of the elements is 0.004 lambda. So you can begin looking at that situation, go ahead and do the analysis, and then once you get the test, you'll see the particular questions that you need to address. And so that completes this related lecture. Again, lectures 11 and 12 are related, and in fact we're going to have still one more lecture in which we will touch on the Yagi Uda array. We probably won't devote all of lecture 13 to it, but we will at the beginning of lecture 13 do still one more type of problem about the Yagi Uda array before moving on to section 4 and chapter 6. So that concludes lecture 12, and good luck.